Okay, everybody, we are in the home stretch. We've made it past the case study. We just have the final exam left. I've heard from a number of you that this has really been a challenge the rest of this semester. And I hate as much as the rest of us that we had to go through this, but we're getting close to the end. I hope that all of your other projects for other classes are going really well. And despite the challenges, I hope that you are proud of what you've accomplished so far and that you're going to be able to get through the next week with finals and then figure out what summer and fall means going forward. Before we jump into multi-criteria decision analysis, I just want to give a plug for the course evaluations again. I've recognized this has been a weird semester, but I still do appreciate your constructive feedback on what you think went well, what do you think we could change to make it better, both after spring break as well as before it. So I hate asking anyone to do any extra work right now, but if you do have the time this weekend, the evaluations close out on Sunday night, and I would be grateful to hear from as many of you as possible on that as well, so that I can make the class better for future years. I also wanted to say that I will be doing a live exam review on Monday morning. We'll do it from 10 to 11 o'clock Eastern Time. And this will be an opportunity to walk through what we've done this semester, ask questions. I may have an example problem or so, but we can talk through in more detail about what the exam is going to look like. It's pretty much the same sort of format as what we saw in the midterm, but obviously the delivery mechanism and submission is going to be a little bit different. So I will also walk through the details of how that submission process is going to work with a practice assignment that you can all practice turning things in online as well. So far this semester, we've seen a couple of different examples where multi-criteria decision analysis would be handy, but we've only really talked about how to incorporate one of them into an analysis. And that's when we were talking about cost effectiveness analysis, where we had a cost as one particular impact of a project, and then we had whatever the primary goal of the project was as something that couldn't be expressed easily in monetary terms. Then we have this direct trade-off between the cost of the project and the effect. And we talked about how to analyze that situation. Last week, we saw another example when we were talking about risk aversion, because we implicitly are evaluating trade-offs when uncertainty is introduced between the expected worth of a project and the variance associated with the uncertainty. In other situations, we might have a large number of different ways that we could configure a project in order to meet different design criteria. Oftentimes, we'll have a design or spec document that lists minimum standards for certain quantities, like the speed of a production line or the quality or the defect rate, things like that. But in some instances, alternative design might go beyond that minimum performance, and so we would want to know how to weigh trade-offs between those different design criteria if they're not all equal to each other. And then finally, we may have some examples of projects that have a mix of monetary and non-monetary impacts. If we're buying a car, for example, I might not put a price tag on the color of the car in terms of how much I'm willing to pay in order for my car, in my instance, to be black, as you might guess, or for the storage space in the trunk of the car. I'm not going to give you a figure that says, well, if this particular car has an extra 10 cubic feet of space, I'm going to pay you another $100 for the car. But I want to know how to incorporate those and my preferences for those into how I should analyze which car I want to buy. So in this video, we're talking about what are called non-compensatory methods for multi-criteria decision analysis. That means that we are not compensating across different criteria. So we're not weighing trade-offs explicitly with these methods. In the next video, we'll talk about compensatory methods of how to explicitly conduct a trade-off analysis, and then we'll have another video showing an example of that. The easiest way to address a multi-criteria decision analysis problem is the concept of dominance. If a project is better than another with respect to every decision criterion, or at least as good, then it's what's called a dominant project. So no other project is better on some criterion without also being worse on at least one other criterion. That basically means that dominance is a really simple way of extending the single criterion case that we've talked about all semester, where the preferred project is the one with the greatest present worth. Now we just have multiple criteria, some of which may not be monetary, and so as long as there's one option that is the greatest present worth for the monetary impact as well as the best in each of the non-monetary impacts, then we have a simple choice to make. Take that one. It dominates all of the others. The nice thing about the dominance criteria is that it doesn't require us to make any assumptions about the relative importance of each criterion. We don't have to know which impact decision makers care the most about. We just can identify that a particular project is better than all the others. This will look really similar to what we saw when we were doing a cost effectiveness analysis. So suppose that we have different options for a production line where we have some fundamental trade-off between the production speed S and production quality Q that we can create with different options of how to set up the line. We could have lots of different possible configurations, and we would represent the speed and quality as a vector of S and Q. Okay, so a solution x1 dominates solution x2 if we're in a situation where fi of x1 is greater than or equal to fi of x2 for each of the criteria. So for criteria 1, which in this case was speed, and criteria 2, which was the quality. This assumes that we're trying to maximize both of those objectives. We would just flip the inequality if it's something that we're trying to minimize, where a smaller value is better. So we dominate x2 if we're at least as good for all of the criteria and strictly better for at least one of them. That means that any particular project that falls within this region that the cursor is floating around in is dominant over x2, and it's also feasible because it falls within our feasible production frontier between S and Q. We can develop a set of non-dominated projects, and that defines what's called the Pareto frontier, where each of these particular projects now in red are not dominated by any other point, and so they make up the Pareto frontier, and we would call them Pareto dominant, or in some cases you would see the term Pareto efficient. If we're accounting for the fact that uncertainty might exist in our estimate of how a particular solution is going to perform, we might also be interested in something called a Pareto approximate set, which means that we're going to take all points within some epsilon of the feasible production frontier, or the Pareto frontier that we can identify for some value of epsilon. We likely are not going to run into a single project that dominates all of the others. In this case, that would be this project in green that is dominant over all of the other projects on the Pareto frontier, but we're kind of outside of our feasible range. One thing to note is that I'm implicitly assuming that these projects are all mutually exclusive from each other. So if I'm going to do one, that means I'm not going to do any of the others. However, if we are in a situation where we want to choose, say, the top 5 project options, maybe what we're evaluating here is that we want to open up locations of a fast food chain, and we have different options for where we could put the restaurant, and we want to open up 5 new locations. So we're going to pick the 5 best. They're not mutually exclusive anymore. If that's the case, A project that's dominated by the best option might still be the second best option. If we can't identify all of the projects that we need through dominance, then that means that we need some other approach to further whittle them down. One way to do this is called lexicographic ordering or lexicographic sorting, which requires us to rank the decision criteria that we have in order of which ones are most important to us. The project that then has the best score on the most important criteria is the one that we take. If there's a tie, then the tiebreaker is always the score on the next most important criterion, and so on down the list. For example, if we're buying a car, we might care most about the price and then comfort and so on. And so we would choose the cheapest car under lexicographic sorting. But if there are two options of cars available with the same price, then we would pick the one that's most comfortable. If they're both equally comfortable, we take the safest one and go on down the list until we have one project remaining. In practice, this really often means that you only have a single criterion because it might be rare that you would actually have a tie on the first criterion. If that's the case, that differences from other criteria aren't going to come into play. So using that lexicographic rule, we have this extreme selection that we would tend to produce. So this is not a particularly common practice. If you think about it, a lot of people would say that cost is the most important factor when they're deciding on a car. But if that's true, and they're using lexicographic sorting, then why aren't they all driving really cheap, old, beat-up cars? This is a clear indication that people aren't really using this technique to make a decision. On the other hand, we have goods like plane tickets, where a large proportion of people do really just take the cheapest option available, even if it means you're not going to have much legroom, it's going to be uncomfortable, it's going to be on a flight that leaves at 5 in the morning, but it's cheaper. However, in a really complex engineering environment, we're probably not going to go with something quite that simplistic. So we need another way to allow for other factors to matter besides just the most important criterion. One way to do that is through a rule called satisficing. And the way that this works is that we just set some minimum threshold of acceptability for a given criterion, and any particular project that meets that threshold is satisficing. And so we can look at our list of projects and just use this to screen out projects that are not acceptable by not meeting that threshold of acceptability. If we have, say, 2 metrics, then our original problem would be to try and maximize the value of both of those metrics when choosing a solution. So we have a 2-dimensional optimization problem that requires some trade-off analysis. We would have to identify the Pareto frontier that is simultaneously maximizing both of those metrics. If we use satisficing on the second metric, whichever one is less important, that changes the problem now to where we still have an optimization problem, but now it's a unidimensional problem. So we're maximizing the first metric subject to the second metric having a value of at least this acceptable threshold, in this case, C. This doesn't always make the optimization problem itself easier to solve. It's just a communication tool or a cognitive shortcut, like bounded rationality says we're looking for. That if decision makers are willing to accept satisficing on one of the metrics, that makes our solution more interpretable. In the used car example, we would now say we have some minimum standard for comfort. For me, that might mean I need enough legroom to get in the car and drive it without getting a cramp. Then, as long as we narrow down our set of options to only cars that meet that standard for comfort, then we would try and take the cheapest option among those that remain. To sum up, Methods like dominance, lexicographic ordering, and satisficing allow us to reduce the complexity of a multi-criteria problem and either reduce the set of alternatives that are under consideration or the set of output metrics that we need to evaluate. In the next video, we'll talk about compensatory methods where we do need to explicitly consider trade-offs between outcome metrics.